Hello class, welcome back. This is the video for section 9.3 of your stats. And I'll be assigning this section 9.3 at the end of today, Wednesday. It'll be due next Monday, which I believe is April 6th. So here we go with this section. Again, just reading through this, the primary difference between large and small samples is that our estimate of the standard deviation is not as reliable. When that occurs, we're forced to use a t statistic rather than a z. That again is assuming the population is approximately normal. The good thing is that our formula for the t is exactly the same one we've been using for our z. It's the sample mean minus our hypothesized mean divided by standard deviation divided by square root of n. Exactly the same as z. Do want to remind you we use that t chart, however. That's that sliding chart, and we use it with n-1 degrees of freedom. We saw this before, that chart. We've used it before. It'll be similar. A few slight adjustments to it in today's lesson. I would like to begin with what I'm going to do occasionally by saying just the numbers. I'm doing that to mainly make the context of the problem eliminated so we don't get confused by it. We're just going to look at the numbers on this particular situation. What I would like you to notice here is that n is 15. That is less than 30, which means we're looking at a small sample. I'm going with just the numbers for a two-tailed test. So here we go with that two-tailed test. Let's go with a critical value test first. They've gave us the null hypothesis and the alternative right up here. So I'm just recopying them down. The mean is 82. The alternative is that the mean does not equal 82. We list our alpha level. Our alpha level is not given, and hence our default is 0.05. We list our sample size, 15. It's less than 30, so that means I'm going to be using a t statistic. That's different than what we did previously. We used a z. Now I need to get my rejection region. Because n is 15, my degrees of freedom will be 14, and I'm using the alpha level of 0.05. But I want to remind you again that alpha level is on a two-tailed test, which means that 0.05 that I'm looking at is split between two tails. I have half of 0.05 in this tail, 0.025, and the other half in this tail, 0.025. That t distribution uses the tails to determine that. So again, before I go to the chart, 14 degrees of freedom, n-1, tail will be 0.025 because it's two-tailed. I split the alpha. So here we go. 14 degrees of freedom, column 0.025. That line in the sand is 2.145. That means that this is a positive 2.145. This is a negative 2.145. Each side because it's two-tailed. We don't need that chart, but I do need to list my rejection region. This rejection region, this tail, is when z is less than that negative number. Z is less than this negative 2.145. Or if it goes over to this rejection region, Z is more than a positive 2.145. So Z is greater than a positive 2.145. That's my rejection region. Again, a little bit different because the T-chart works with the tails and we have n-1 degrees of freedom. So now I go to step 3. The T formula is the same formula, x bar minus the mean divided by S over the standard deviation. So in this case, when I substitute in, my sample mean was 79.52. The hypothesized mean was 82. It's going to be a negative, which means I'm going to be on the left side here. Divided by the sample standard deviation, 5.15. Divided by the square root of n, square root of 15. Again, you need to be able to use your calculator to get through that. Turns out to be a negative 1.865. I could have rounded that up to a negative 1.87 as well. But the key is that it's not less than a negative 2. This negative 1.86 is about over here someplace. It's not over our line in the sand. That means I have insufficient evidence. So my concluding would be T equal to a negative 1.865 is insufficient evidence to reject the null. And thus, we continue to assume I'm going to continue to assume the null hypothesis. That would be that the mean is equal to 82. Notice normally we would write this in context of the problem, but because there was no context here, I just said we continue to assume the null, which is 82. Let's also now look at a p-value test for this same one. It would again be the same null and alternative. Step number 2, I would have listed the same default alpha, n equal to 15, and a t statistic. I would not have listed the rejection region because it's a p-value test. I would have calculated the t the same manner. Rather than writing it all out, I'm going to go with the negative 1.865 right away. But now I have to find the p-value. This is a little bit trickier now with these. So we need to watch carefully once where I'm getting some of these values from. Watch this next procedure carefully now. It's a two-tailed test, so that P is going to be a 2 times the probability of the tail being a negative 1.86. I'd like to remind you again, I'm looking at degrees of freedom 15 minus 1. Now try to remember this 1.865. I need to work only in row 14 because I had a sample size of 15. You remember we got 1.865. I would like you to notice that 1.8 is between this number and that number. 1.8 falls between these two numbers in the row 14. Well, any number that falls in between these two numbers has got a probability between 0.05 and 0.025. I'm going to say that again. Any number that falls between these two t-scores has a probability in the tail of somewhere between 0.05 and 0.025. I don't need to know exactly where it is in between. I just realize that it has to be somewhere in between. So because it's between those two numbers, watch how I'm going to write this now. My probability is between these two numbers. 0.025 is actually less than 0.05. So I'm going to put that on this order, the smaller one on the left, 0.025, and 0.05 on the right. That means once I double it now, I'm going to take 2 times all of this. My p-value, when I double that, will be an 0.05. Doubling 0.05 will make it into 10. My p-value is somewhere between 5 and 10%. Might be 6%, might be 7, might be 8, might be 9%. We don't know exactly, but it really doesn't matter that we don't know exact, because when I'm running a p-value test, I compare the p-value to alpha. This p-value is more than 5%, which was my alpha. If it was less than 5, I would have sufficient information to reject. But if it's more than alpha, which it is in this case, we don't know how much more, but we know that it is more, I have insufficient evidence. So step 4 would be to run this p, 0.05 to 0.10 is insufficient evidence, and the rest of it would be the same. Again, insufficient evidence, thus we continue to assume the null. This p-value was a little bit trickier again. So I took that 1.865, found that it was between these two numbers, which meant my tail had to be between 2.5% and 5%. Because it was two-tailed, I doubled that. That's a little tricky. We'll have more examples to show that in just a moment. Another example. Giving you some time to read it. I'm wondering if my electrical contractor is charging me, the general contractor, more than he's supposed to. He's saying it's 500 yards of electrical wiring for each new home. And I'm wondering, is he actually using 500 on the average home? Or is he using a lot less and still charging me for 500? I'm testing basically is 500 accurate. Okay? Do I have any evidence that it is not charging me the correct amount in this case? We're assuming here a two-tailed test. So I'm going to show both again. Critical value. And a p-value. Again, in your assignment, almost always you got to do just one or the other. Two-tailed test, however, is the 500 accurate? That's my null, mu equal to 500. My alternative would be that it does not equal 500. Over here would be exactly the same. Step number 2, I list my alpha level. Again, it didn't give me an alpha level, so the default is always 0.05. Same thing over here. My sample was 15. That's less than 30. So I have to use a t statistic. Sample over here, same thing, 15 t statistic. Step number 3. I'm sorry, before I do that, I need to get my rejection region. Okay, I'm going to be in row 14 again. Happens to be the same one that I did last time. N minus 1, 15 minus 1 is row 14. I'm going to take my alpha and split it into 2 tails. So again, you don't need this drawing, but it might help you understand what I'm looking at. My rejection regions are this tail and this tail. The alpha is split into each one of those. So this 5% is split up into 2.5 and 2.5. I'm looking for those t-scores. They're going to be my rejection regions. So I'm going to go to row 14, column 0.025. Happen to be the exact same one of last time. Row 14, column 0.025 was 2.145 again. That's those t-scores. One's positive, one's negative. Those are my lines in the sand. So I need to say one rejection region is to the left of this. Z has to be less than the negative 2.145, or Z has to be greater than the positive one, 2.145. That's my rejection region. Then I calculate my t-score. It's the same formula, x bar minus the mean divided by s over the square root of n. So my sample was 454.7 minus the hypothesized 500 divided by the standard deviation 166.4 over the square root of 15. When you do that calculation, turns out that the t actually turns out to be a negative 1.05. Okay, well, if you look at that, that's not over my line. A negative 1 is about over in here someplace. It's within reasonable variance of the 500. It does not give me sufficient evidence to doubt the 500. So I'm going to have insufficient evidence, so I need to write that out now. So step number 4, t equal to a negative 1.05 is insufficient evidence. To reject our null. And thus, we continue to assume in context now, we continue to assume the mean or average amount of wiring needed is this 500 yards per home. Going to the p-value now, I would have found the same t-score. I would have put the entire formula and substitutions in, but for time, I'm just going to go right to the value. But now I need to get that p-value. Okay, because it's two-tailed, I need to double, and I have to find what it's between. I'm going to be looking for the negative 1.05 in row 14. So again, I'm stuck in row 14, find negative 1.05. Well, the negative 1.05 would be between those two numbers. Okay, well, my chart here is a little bit more precise than yours. I believe the one in your back of your book only goes up to 10%. So basically, you're saying this number is going to have a probability that is greater than 10%. I think the last one you have is this one, 1.345, and yours is smaller than that, which makes it greater than 10%. So you're just going to have greater than 10%. X is greater than 10. When you double it, you're going to have X to be greater than 20%, which is obviously not less than 5. It needs to be less than 5% for me to have sufficient evidence to reject. It's not. Makes it insufficient evidence. So step 4, P is equal to, or I'm going to put down just like this once, greater than 0.2 is insufficient evidence, and the rest would be the same as what I wrote over there. A little tricky with the p-value. If they don't specify, usually the rejection regions are easier for most students, but some people still prefer the p-value one as well. Give you a chance to read through that one once. It doesn't specify what type of test they wanted me to run. That means I could go with just a critical value, or I could go with just a p-value. I would not have to do both. Again, just for your repetition, I am going to choose to do both yet. But if this were in your text, you would only have to do one of these. After 18 weeks, 18 is a sample that's less than 30. That's what's screaming at me, small sample test. We're looking to increase the sales. We're wondering, should I continue to use the advertising? We're wondering if the advertising is paying off, because that's what we're hoping to happen. We're hoping to increase the sales. That's screaming at me, single-tailed test. So to that end, I come up with my alternative first. I want it to be increasing over that. So I want it to be more than 5,775, greater than 5,775. The opposite would be that it is less than or equal to 5,775. You could have just put equals there. But this one, the alternative, had to be greater than. That's crucial. Step number 2. The alpha level, they've asked us to do 2 of them. So I'm going to go with 0.05, and I'm also going to go with 0.10. We have n equal to 18, which means I need to use a t-stat. Now I need to have 2 rejection regions here. One of them will be for 5%. It'll be on row 17, 18 minus 1. Degrees of freedom will be 17. One will be 5%. One will be 10%. But now notice, this again is crucial here. Easy place to make an error. I'm looking to see if it's greater than that number. The alternative here means I'm testing on the greater side. That means to the right of 5775. My line in the sand is on the right side. I'm looking for that t-score. What is that one going to be? That means it's going to be t greater than some t-score for 5%. Notice carefully now, listen carefully please. The alpha is entirely in that tail because it's a single tail. It's not 0.025 here, it's all 5% got put in there. Well, what is that particular t-score? It would be in this 5% column, 1.74, row 17. 1.74 is that t-score. That's my first line in the sand, 1.74. But because I had 2 alpha levels, I've also got to consider putting all 10% in the tail. That'll give me another rejection region. All 10% in the tail is when I have that column, 1.333. That's my other rejection region. On a single tail, listen carefully to this. This is such a common mistake. For a single tail, if mu is greater than the number, then your rejection region has to be greater than a positive. On the other hand, if the alternative for a single tail was mu is less than, then these would have been less than a negative. It would have been on the other side. These two things have to work together. They have to both be on the same side. That's important. It's an easy place for a lot of students to make an error. Then I calculate my t. Same old formula here. My sample mean was 6,012. Hypothesized mean 5775. Standard deviation 977 divided by the square root of 18. Turns out that that t-score happens to be 1.03. 1.03, back to my chart here, 1.03 is not over that line, not over either one of those lines. 1.03 is back here someplace. It's within reasonable variance of that number. Therefore, it's not enough evidence for me to doubt the original 5775. Consequently, t equal to 1.03 is insufficient evidence to reject the null, and thus we continue to assume the mean, in this case, what is it standing for? The mean weekly sales are still the previous average, 57.75, and in this case, the advertising has not paid off. The p-value would have had the same null and alternative. I would have listed both alpha levels, same sample size, same statistic. I would have calculated the same t, 1.03, and now the p-values. Notice this time there's no doubling effect because it's a single-tailed test. So it's 1 times that x value. I need to use the chart again to find what this 1.03 will be between. I'm going to be in row 17 again. Remember 1.03. Notice 1.03 here falls between these two numbers, kind of crossed out. Basically, it's going to be to the left in your book of 1.33. It does not fall in between here, it's to this side, which means it is more than 10%. So it is more than the 10%. We don't need the rest of this for that example. That means P is greater than 10%. Because it's greater than both my alpha levels, I cannot reject at either one. I do not have sufficient evidence at either alpha level. So therefore I say P greater than 0.10 is insufficient evidence. Same as what I had over here. If I had ran a second flight of advertising, maybe continuing, and looked at it after 30 weeks, after 30 weeks, gotta find it here a moment yet, I apologize. What would have changed? Well, if 30 weeks had been used instead, I'm still looking at the same alpha levels, but I would have had 30 here, which meant a z-stat. Then I would have calculated my rejection regions using those two alpha levels with a z. Then I would have calculated a z-score. Had I done that, the z would have in this case been 0.94, even smaller because of a larger denominator. It would not have been in a rejection region, and I would not have had enough evidence. I would have also had insufficient evidence to reject the null. Had I taken a 95% confidence interval with 30 weeks, this takes you back to the last chapter, it would have been X bar. Because of 30, it would have been a z-score, S over the square root of n. Plugging all of those numbers in, I would have had a couple of different ones, but I'm going to go with just the 95% one. It would have turned out to be 56.62 and 63.61. Notice that this interval contains, I want to emphasize this again, contains the 57.75. If the interval was entirely below 57.75, I would have had evidence that it's dropped. If this interval had been entirely above, that would be evidence that it had increased and the advertising had paid off. But my interval was on both sides of 57.75. 57.75 is in between here. It means that I don't have evidence that this interval is entirely above or below, which is why, again, I would have to continue to assume 57.75 is still accurate. Our last problem. Well, I've given you a chance to read it. This particular problem is a little different in that they gave me the raw data, 17 scores. That's, again, screaming at me, n equals 17, which is a small sample. I've got to use a t-statistic. They've given me an alpha level. What is different about this is that you are expected to come up with the sample mean, x bar. You are also expected to come up with the standard deviation of that sample. You would need to plug that into your calculator, and it turns out that the sample mean would have been 2.206. The standard deviation would have been 0.967. You may get some like that in your book where they give you the raw scores, and you got to find both of these from your calculator. Again, make sure that you can do that in your calculator. Okay? They did not tell me what type I had to use. And with small samples, I think it's easier to use the critical value test. So I'm going to go with just that one. So step number 1. Got to decide if this is a two-tailed or single-tailed. We're being assured that they can reduce the average time below 2.5. I want to see if there's evidence to support that. Because I'm trying to support that, I'm going to make my mean below the 2.5, less than the 2.5. This one I could put greater than or equal to. I'm just going to go with equal to 2.5. If you had greater than or equal to there, that would be fine. I'd accept either one. But this one, the alternative, has got to be less than 2.5. That's what I'm trying to show. Step number 2, alpha level 0.05. Sample size 17 scores here, which means I need to use a t-stat. Step number 3, the formula, x bar minus the mean, s over square root of n. Sample mean was 2.206 minus the hypothesized mean, 2.5, divided by standard deviation, which we found in our calculator, 0.967, divided by square root of the sample size, square root of 17. Turns out that that t-score is a negative 1.251. I apologize here. I forgot to get my rejection region in step 2. So I'm going to go back and get that now. The rejection region, it's single-tailed. So that means basically what I'm talking about there is this. Single-tailed, 2.5 is the average time. But I'm looking at, notice carefully now, I'm trying to show that it's less than 2.5. That means that my rejection region, if it's less than 2.5, it's to the left of 2.5. This is my rejection region right in there. I want that to be all of the alpha because it's a single tail. What then is that t-score? That's what I got to find on my chart. So I'm going to be looking for the 0.05 column, row 16. Here's row 16, 0.05 column, 1.746. That's this t-score, but it's negative. It's on the left side. So my rejection region is t has got to be less than a negative 1.746. A common mistake right up here, people would have said t is greater than a positive. They would have been testing the line in the sand over here. That's not what we were looking to show in our null alternative. That would have been a crucial error. Okay, well, we already calculated our t. It's not in the rejection region. The 1.2 is about over here someplace. It's not over the line. Consequently, t equal to a negative 1.251 is insufficient evidence, et cetera, et cetera, et cetera. You'd write out. You would have to say, I don't believe their firm has in fact reduced our average of 2.5. We don't have evidence to show that. Wanted this example mainly to show sometimes they give you the raw data. You got to figure out your own sample average and your own standard deviation. Also, I of course would have had to assume here that this was a normal distribution. One way I could have shown that would have been to make a stem and leaf chart. And you see that this is somewhat of a mound-shaped distribution. That would have allowed me to use that t-score. Again, that's all we have for today. We're going to be assigning section 9.3 this Wednesday, making it due next Monday, which I believe is April 6th. Have a good rest of your day.